To verify this, we're going to use the irreducibility of the representation. Since we have verified 1, 2, and 3 in the statement theorem with n replaced by lambda naught, this already guarantees that the subspace capital V naught defined by the span of V naught V1 through Vn naught is preserved by pi of h, pi of e, and pi of f. Remember, little SL2C is spanned by h, e, and f. This shows this capital V naught is a pi invariant subspace. So, this tells us that pi naught, which is defined as a representation from SL2C to the endomorphisms on V naught, capital V naught, is a sub-representation of pi, which is from SL2C to the endomorphisms on V. So this is a sub-representation of this. But pi, we know pi is irreducible. So there are only two cases for sub-representations. This pi naught is either 0 or same as pi. But we know pi naught cannot be 0. That is because those vectors are non-zero. So this V naught cannot be 0. So pi being irreducible implies pi equal to pi naught, V equal to V naught, and n equal to n naught. Remember, n plus 1 is a dimension of V, and n naught plus 1 is a dimension of V naught. So n must be equal to n naught. This verifies this part of the equality. Next, we're going to look at this lambda naught. We'll show that lambda naught is n. To this end, we're going to invoke the notion of trace. Now, since the formula H is same as E lib bracket F, now we look at the trace of pi of H. This is equal to the trace of pi of E lib bracket with F. Which, because pi is a Lie algebra homomorphism, this is equal to but remember from linear algebra, for two square matrices or two linear transformations A and B, the trace of their product is equal to the trace of their reversed product. Trace of AB is same as trace of BA. So they are equal, which give us 0. So the trace of pi of h is 0. But on the other hand, the trace of pi of h can also be computed through its eigenvalues. So trace is equal to the sum of eigenvalues of pi of h. What is the sum of eigenvalues of pi of h? This is the sum of lambda naught minus 2i's from I equal to 0 to n of lambda naught minus 2i. This is from 1. And now we're just gonna add this up. This is n plus 1 times lambda naught minus n times n plus 1. Now compare this guy with 0. This is equal to 0. So we get n plus 1 times lambda naught minus n times n plus 1 equal to 0. This forces lambda naught equal to n. Okay, now, are we done with the proof of the uniqueness and the moreover part? Are we done yet? Actually, we are indeed done with the moreover part. We have shown for this given V that there is a basis satisfying the properties 1, 2, and 3. We have done this. But there's a little bit more for the uniqueness part. To complete the uniqueness, we better show that for each integer n, pi and pi prime, and v prime, with v and v prime's dimensions all equal to n plus 1. Then those two representations are equivalent. That part is easy, but we have to show that. So let me write this down. So far we have showed the moreover part and the uniqueness for the fixed vector space V. The uniqueness of the representation for the fixed vector space V of dimension n plus 1. Now suppose we have two irreducible representations. Of dimension n plus 1 of little also 2c. One is denoted pi 1. This is a representation of SL2C on V1, and pi 2 representation of SL2C on V2. But V1 and V2 are both of dimension n plus 1. So we want to show those two representations are equivalent. This is not hard at all. But what we have done, we can find the basis V0 j, V1 j through Vnj for the vector space Vj, where j is equal to 1 or 2. We find the basis for each of those two vector spaces, such that we can choose such a basis in such a way that we're still going to have those three properties. Here again, j is equal to 1 or 2, and I is from 0, 1, 2 through n. Now we define a vector space map from V1 to V2, sending the basis vector Vi1 to Vi2 for I equal to 0, 1 through n. And extend this from the basis to any vectors on V1. This is clearly an isomorphism. And you look at the following diagram. This diagram is commutative because if you replace this dot by H, E, or F, then you can verify the diagram is commutative on the basis vectors. And as a result, this is commutative for all vectors in V1. So this diagram is commutative. Because E is an isomorphism. This means pi 1 and pi 2 are equivalent. Now this finally finishes the uniqueness part and the moreover part.